Before Einstein, space and time were thought to be separate, rigid, and absolute, like the stage upon which all events played out. But in the early 20th century, one man shattered that illusion. He revealed that space and time are woven together into a single cosmic fabric, spacetime, and that this fabric bends, stretches, and warps with mass and motion. This is the story of how two revolutionary theories, special relativity and general relativity, reshaped our understanding of the universe. One describes how time slows and lengths contract when you move near the speed of light. The other reveals how gravity is not a force, but a curvature in spacetime itself. Before we get too deep into this topic, be sure to like this video and subscribe to the channel. This helps to bring more valuable content to the platform for your knowledge and understanding. Remember, knowledge is power. Now back to the episode. At the turn of the 20th century, Isaac Newton's laws reigned supreme. His concept of absolute space and time explained everything from falling apples to planetary motion. But as physicists explored electromagnetism and light, cracks began to appear. The Michelson-Morley experiment of 1887 found no evidence of the luminiferous ether, a mysterious medium once thought to carry light waves. Light, it seemed, didn't need a medium at all, and its speed was constant. This discovery would shake physics to its foundation. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published 4 papers that would change everything. Among them was On the Electrodynamics of Moving Bodies, the foundation of special relativity. Einstein proposed 2 radical ideas. The laws of physics are the same for all observers in uniform motion. The speed of light in a vacuum is constant for everyone, no matter how fast you move. From these simple postulates came astonishing consequences. Time dilation, length contraction, and the most famous equation in history, E equals mc squared, showing that energy and mass are interchangeable. Special relativity wasn't about gravity yet. It was about motion, light, and the nature of reality itself. Einstein's former mathematics teacher, Hermann Minkowski, took these ideas further. In 1908, he declared that space and time were not separate entities, but part of a unified 4-dimensional continuum called spacetime. He famously said, "Henceforth space by itself and time by itself are doomed to fade away into mere shadows." This geometric view set the stage for Einstein's next leap, a theory that could explain acceleration and gravity. Einstein realized that if acceleration could mimic gravity, a principle he called the equivalence principle, then gravity itself might not be a force at all. After nearly a decade of intense work, he unveiled General Relativity in 1915. The theory showed that massive objects like stars and planets warp spacetime, and that this curvature tells objects how to move. To test it, astronomers observed starlight bending around the sun during the 1919 solar eclipse. The result matched Einstein's predictions perfectly, and overnight, he became a global icon. Gravity, it turned out, was geometry. So what separates special from general relativity? Special relativity deals with motion at constant speed. No gravity, just straight lines through spacetime. General relativity includes acceleration and gravity, where those straight lines curve. One applies to the micro-world of motion, the other to the cosmic architecture of galaxies and black holes. Both share the same foundation, the invariance of light and the relativity of time and space. You experience Einstein's legacy every time you check your phone. The GPS satellites orbiting Earth must account for both types of relativity, special because they move fast, and general because they're farther from Earth's gravity. Without relativistic corrections, your location would drift by kilometers each day. Relativity also governs particle accelerators, where subatomic particles approach light speed, nuclear energy through mass-energy equivalence, and cosmology, shaping our understanding of black holes, gravitational waves, and the expanding universe. Even your digital camera owes thanks to Einstein's work on the photoelectric effect, which won him the Nobel Prize in 1921. Yet Einstein's journey didn't end with general relativity. He spent decades seeking a unified field theory, a single framework to connect gravity with electromagnetism and, by extension, quantum mechanics. Though he didn't succeed, his search paved the way for string theory, loop quantum gravity, and quantum cosmology, the modern frontiers still trying to reconcile the quantum and the cosmic. Einstein's two theories remain pillars of modern physics. Special relativity underpins quantum field theory. General relativity anchors our cosmic models. Together, they define our place in the universe. Today, more than a century later, Einstein's equations continue to predict and inspire. From the ripples of gravitational waves detected in 2015 to the first black hole image captured in 2019, we are still witnessing the echoes of his genius. Special relativity taught us that motion alters reality. General relativity taught us that mass shapes space and time. And together, they remind us that the universe is not static. It's alive, dynamic, and intimately connected. The deeper we look into space, the more we see the curvature of thought itself, Einstein's vision made real. If you found this content helpful, don't forget to like this video and subscribe to the channel. Leave me a comment. Let me know what you think about how special and general relativity have shaped our world today. Join me next time for another deep dive into the mysterious world of quantum physics and the cosmos.